Alright, so today we're going to be learning about logarithmic functions. Last class we learned about exponential functions, so the next topic is logarithmic functions, and they're actually pretty closely related. Before we do that, I'm going to go ahead and recall inverse operations. Addition, the inverse, remember inverse just means opposite of addition is subtraction. Multiplication, the inverse or opposite operation is division. If I want to square something, the opposite operation would be square root. There's a couple more. I could do cube and cube root, etc., but I just listed a few. So in showing those, for example, let's go ahead and start with the first one. We have x plus 2 equals 10. If I wanted to solve for x, I would have to use an inverse operation. And what I mean by that is, right now we have x plus 2 equals 10, and the question says to solve for x. So in order to solve for x, you would have to use inverse operations. Right now, x is adding 2. So the inverse operation of addition is subtraction. So we would use the subtraction operation by subtracting 2 from both sides. 2 take away 2 is 0, so those just cancel out. And we're just left with x equals 10 minus 2, which is 8. On the next problem, we have 2 times x equals 10. And if I wanted to solve for x, I would use the inverse operation of multiplication. Right now, 2 is being multiplied by x. So in order to get rid of the 2, in order to get x by itself, you would use the inverse operation of multiplication, which is division. So in order to get rid of this 2, I'm going to divide both sides by 2. 2 divided by 2 is just one whole. So I'm just going to cross them out. You can write 1x or you can just leave it off. And x equals 10 divided by 2, which is 5. And there's your answer. Next one, we have x squared equals 9. I want to solve for x, so I need to get rid of this second power, this exponent of 2. Well, the inverse operation of square is square root. So if I just wanted to get rid of the square, I would square root both sides of the equation. X squared and square root of x are inverse operations, so they cancel out. And I'm just left with an x equals square root of 9 is technically positive or minus 3. Because 3 squared is 9 and negative 3 squared is also 9. And there's our answer. Alright, this next one gets a little tricky. We have 2 raised to the x power equals 8. And I want to solve for x. So the goal here is to get x by itself. We want to get rid of this 2, but the 2 is a base. The 2 is not the exponent like it was on the previous problem. So our question here is, what do we do to get rid of this 2? What do we do to get x by itself? Now, a lot of students might guess, oh, well, don't you divide by 2? No, because 2 is not being multiplied by x. 2 is being raised to the power of x. So I can't divide by 2 because multiplication is not happening. Another common guess would be, well, couldn't we take the square root? It's not raised to the second power. It's raised to the x power. We were only able to do that because x was raised to the second power, and so we took the second root, also called square root, and those are inverse operations. But here that is not the case. We actually haven't learned about an operation that undoes this type of exponential equation, but that's what we're learning about today. It's called logarithms. So right now we have an exponential equation. It's called exponential because x is in the exponent area. And the way we would undo exponentials is we would use something called a logarithm. I'm going to fill that in the blank. To help us solve exponential equations. Now there's a whole bunch of applications of logarithms, and there's a much deeper definition and proofs that go into logarithms. But for this course, we just kind of skim the surface. And what I really want you to take away is just that logarithms are just the inverse operation of exponentials. We use logarithms to undo exponentials. So we'll do examples like this in just a bit. But just know that we are going to have to use a logarithm. To undo this, which we'll kind of skip back at the end, but I'll go ahead and move on for now so we can do some examples before trying to do that problem. Here's the formal definition, the textbook definition I got from the textbook of what a logarithm is. It is generally written as a log, L-O-G, and you'll even see it as a calculator function right here. I know mine is right here. L-O-G is short for logarithm. And if you notice, I'm going to write this a little larger. Right now it says y equals log. And then there's this little tiny a. That's called our base. It's written on the bottom on purpose. It's written kind of tiny because it's called the base. So log base a of x is how I would read this equation. Okay, and that's the general form of a logarithm. Y is equal to the logarithm to the base a of x is another way to read it. I always read it as log base a of x. Now there's a few different things to keep in mind, and that is that the base has to be positive. That's just a general rule for all logarithms. The base has to be positive. So whatever this a value is, whatever it may be in the examples we're going to do, it has to be a positive number. And the other thing is that whatever is inside the logarithm, so I guess in our case is x, it has to be positive as well. So the number or the value inside the logarithm has to be positive as well. So just remember those two important pieces of information, because those are going to be pretty useful when we do some examples in a bit. Okay. All right, let's go ahead and do an example working with exponential statements. So we are given 3 different exponential equations. They're all exponential equations because they have a base and an exponent equals some value. And the goal is to convert these to logarithmic statements. So we're not changing the value, we're just writing it in a different way. Think of it as writing another language. Right now it's given to us in English, and we're going to translate it to Spanish. It's just another language, it's another form that we can write it in. So let's start with question number 8. We have 1.2 raised to the 3rd power equals m. Yes, technically we could solve that, so we could use a calculator, but the goal here isn't to solve, it's just to convert it to logarithmic form. So the way we would write this in logarithmic form, every exponential has a logarithmic form, would be log, start with the base. Now the base is pretty easy to identify. The base is whatever number has an exponent written on it. Well, 1.2 has an exponent of 3, so you know that your base is 1.2. So that's going to be this little tiny number on the bottom, log base 1.2. That's going to be our a value. Of, well, it's always going to be log base 1.2 of, it's kind of like a little, goes around to the other side of the equation, of m, and you can put in parentheses, I kind of just leave it as is, equals, it always equals the exponent. So the exponent is 3. It's kind of like, it does a little roundabouts, a little loop-de-loop. So log base 1.2 of m equals 3. And what we have is we have a logarithmic equation. It's an equivalent statement. It's just written in a different form. We got it from exponential form to logarithmic form. So this would be our answer. Okay. I want to just get us practice with converting between exponential and logarithmic form before moving on, because that's going to really help us. Just this skill alone is going to help set you up for the next few chapters. So really make sure to just get practice with converting from logarithmic form to exponential and vice versa. All right, next one, part B. We have e raised to the b power equals 9. Don't worry too much about what's e, what's b. We're just converting it to logarithmic form. So I'm going to go ahead and set it up by writing log, short for logarithm. My base is whatever has an exponent on it. Now, the only thing that has an exponent on it is e. So e is our base. So e is going to be this little term, this little value here on the bottom. And it's written smaller on purpose. Of 9 equals the exponent, which is b. And there's our logarithmic form. Okay. Same thing for the next one. We have log, my base is whatever has an exponent on it. So the only thing that has an exponent on it is a. So our base is going to be a. Of 24, that's what the equation is equal to. And then set it equal to the exponent, which in our case is 4. And there's our answer. All right, So we've just finished converting from exponential statements to logarithmic statements. The next part, example number 2, we're going to do the opposite direction. We're going to convert it from logarithmic statements to exponential statements. I can use a different color. Or I can use the same. Alright, so example number 2 gives us, we have 3 different logarithmic equations, and we want to convert them each to exponential statements. So I'm given the log form. The first thing we're going to do to convert it to an exponential equation is start with the base. The base is the little number on the bottom, which in this case is a. You're going to raise it to the 5th power and set it equal to whatever's inside of the logarithm, which is 4. So it's still kind of that same little roundabout, little loop-de-loop process. And there would be our exponential equation. So these are equivalent statements. One's just in log form, one's in exponential form. Next one, part B, start with your base. It's the little number on the bottom, which in our case is e. Raise it to the -3 power equals b. Now some of you might be thinking, I thought you couldn't have any negative numbers. The base has to be positive. The base is e is positive, and the value inside the log, which is b, is positive as we know it, we're going to assume. So the -3 isn't really any of those two things, so we're still okay. That's okay. The exponent can be negative. That's about it though. And then last one, part C, start with the base, which is 3. Raise it to the c power and set it equal to whatever's inside the logarithm, which is 5. And there's our exponential equation. Okay. All right, moving on. So example number 3, it gives us 2 logarithmic expressions. Now these are not equations because they don't say equals a number and we have to try to solve for it. Instead, it just gives us a single expression, log base 2 of 16, and we have to figure out what that equals. Now before you go and try to use your calculator, there's no way to type those in, at least not on my model, and most models don't have that unless you have a super high-tech computer. Some of them I have heard of doing that, but we can't calculate that, and that's fine. This one's actually pretty simple. What this is asking, if you think about how could I convert it to exponential form, this is asking us to figure out what is the value of this. Well, log base 2 of 16, it equals something. We don't know what that something is. We want to figure out what is that something. We can set it equal to x. Say this is equal to x. We're trying to figure out what is x. What is this whole thing equal to? Well, if you think about it, if we try to convert it to exponential form, just like we did on the previous page, this would be written as 2 raised to the x power equals 16. And this is an exponential equation, and now we just have to think 2 to what power is going to give us 16? You can kind of play around. Let's kind of try it out. 2 squared, no, that's 4. 2 to the 3rd power, no, that's 8. 2 to the 4th power, hey, there's 16. So x is equal to 4. And that would be our answer. Or really, you don't have to put x. You could just say this whole thing equals 4. Because it never really gave us an x. We just kind of named it x. Okay. All right, same thing for the next one, part B, log base 3 of 1 over 27. What is the value of this entire expression? Well, we don't know what this is. I want to figure out what this whole thing equals, so let's go ahead and set it equal to some number. You could use x. You could use pretty much whatever letter you want. You could even put a question mark, which I'll just go ahead and use x, because that's what we'll be using. And I want to figure out what is x equal to? What is the whole thing equal to? Well, if I rewrite this in exponential form, this would be written as 3 raised to the x power is equal to 1 over 27. And I have to figure out what number, 3 raised to what number is going to give us 1 over 27. Now that one might be a little harder, but let's go ahead and try out some numbers. 3 to the 2nd power, no, that's 9. 3 to the 3rd power, that's 27, but I wanted it to be 1 over 27. Now this might be a little bit of a review from early algebra to figure out how do we make it equal to 1 over 27 instead of just 27. Well, if you're not sure, let's go ahead and play around with some more numbers. Let's try 3 to the -1 power. Let me go ahead and make that a fraction. Math, enter, enter. No, that's 1/3. 3 raised to the negative second power. And I'm going to make it give me a fraction. Sorry, let me retype. 3 raised to the negative second power. And I got 1/9. 3 raised to the negative 3 power. And I got 1/27. So the x value is negative 3. So this whole logarithm is equal to negative 3. And there we go. So for these problems, you're really just thinking 2 to what power is going to give me 16? Well, 4. 3 to what power is going to give me 1/27? That's negative 3. Okay. All right, moving on to the next part is domain and range of exponential functions, or just domain, I believe, for these. Yes, domain of logarithmic functions. Now, the domain of the most basic logarithm, so log base a of x, just has a domain of 0 to infinity, as well as the range. But as you change this logarithm, as you add transformations, as you see how we added 3 on this one, we're doing other things, then the domain and range will change a little bit in its course. But the most basic logarithm, log base a of just like an x value, would just be this domain and this range. But the key thing is the domain of logarithmic functions consists of positive numbers only. And we'll do some examples. All right, so example 4a, it says find the domain of this function, log base 2 of x plus 3. So if I were to graph it, if I could see it, it might be a little easier, but I can't type that in. Now what that is asking, what does domain mean? Domain just means what x values can we use? Are there any exceptions? Are there any x values that won't work, that you won't be able to plug in, that'll give you errors or undefined values? That's pretty much all it's asking. Now, one thing that I said earlier is, remember, logarithms have to have a base that's positive, which on all these we have positive 2, positive 5, positive 1/2, so we're okay. And the other thing is that the value inside the logarithm has to be positive, and that's key. So x plus 3, that's the value inside the logarithm, that has to be positive. So I know that x plus 3 has to be positive, meaning greater than 0. Not even equal to 0, it has to be strictly greater than 0. So we have this inequality that we know has to be true. We're just going to solve for x. I'm going to start by just subtracting 3 from both sides. Plus 3 minus 3 cancels. And I'm just left with x is greater than 0 minus 3 is negative 3. So my domain is pretty much just x has to be greater than negative 3. And there would be our answer. Now you can write it as x is greater than negative 3. Some people might prefer writing it in interval notation, so you can write it as negative 3 up until infinity, just pretty much everything that's bigger than negative 3. Either way is fine. I'm not sure which way it takes on my math lab, or I might take both, but I'll go ahead and just write both methods in case you want to write one or the other. And there's our domain, and all that's saying is that we just have to have an x value that's greater than negative 3 for this function to work. All right, next one, part B, same thing. In order to find the domain, we just have to figure out what x values are going to give me this entire term as a positive value. Now this one's a little bit more intricate because it has a whole fraction. It says 1 plus x divided by 1 minus x, and we want to figure out, we know that this whole thing has to be bigger than 0. It has to be a positive number. Okay. Well, there's 2 parts to it. So in order for this whole thing to be positive, there's going to be 2 cases. Both the numerator has to be positive, 1 plus x, and the denominator has to be positive. So pretty much you're just going to set up 2 inequalities. In order for this whole thing to be positive, the numerator has to be positive and the denominator has to be positive. So they both have to be greater than 0. And then you can just solve for x in each one. I'm going to subtract 1 from each side so I can get x by itself. And x is greater than 0 minus 1, which is negative 1. There's part of the answer. And the second part, I would have to solve for x on this other inequality as well. I'd probably just add x to both sides. And 1 is greater than 0 plus x is x. So we have 2 inequalities. It's not wrong if you leave it like that, but in order to write it as one big inequality, this is just saying x is greater than negative 1. and x is smaller than 1. So pretty much x is bigger than negative 1, so think of like a number line. X is bigger than negative 1, so meaning everything over here and on. And this second one is saying 1 is bigger than x, so x is smaller than 1, so everything before 1. So pretty much everything between these two numbers. So as one entire inequality, you could just write it as negative 1 is less than x is less than 1. Just so you don't have to have it written as two separate inequalities. This is these two statements are the same as writing it as one statement. See how the alligator's pointing at the negative 1, and the alligator's eating the 1. Same thing here. Alligator's still pointing at the negative 1. Alligator's still eating the number 1. Okay. And there's our domain. I should probably write that as. If you wanted to write it in interval notation, you could also write it as negative 1, comma 1. Either way is fine. Okay, and then last one, we have h of x equals log base 1/2 of absolute value of x. Now the only thing that we need to keep in mind is that whatever's inside the logarithm has to be positive. Now this is actually an absolute value sign, these little two fancy bars. This is an absolute value, in case you don't recall. And absolute value bars just means that whatever x is, this whole thing is going to be positive. It means the distance from 0. So technically it's already positive because no matter what number you put inside these two absolute value bars, the result will be positive because that's what absolute value bars mean. The only thing that we cannot have this x being is 0 because it has to be positive, meaning strictly greater than 0. So for this last one, this one would just be x cannot be 0. Any other x value you want to plug into this will still give you a valid positive output value other than 0, because 0 is not positive or negative, it's just 0. So that would be our domain. And there's our answer. Okay, moving on. All right, the next part is graphing. So I'm going to go ahead and show you just real quickly how to graph a logarithmic function. How would we graph this? Since we can't really use graphing calculators for most logarithmic functions, at least not yet. We haven't gotten quite that far. Up here on top, though, I've just listed, these are some textbook properties of logarithmic functions. The domain is a set of positive numbers, which we kind of did a little bit above right now. All logarithmic functions, the x-intercept of the graph is 1. That's just for this, we're just talking about this most basic logarithmic function. Log base a of just an x value. There's no y-intercept. The y-axis is the vertical asymptote. So just some information about the most basic logarithmic function. Now this might change a little bit if we add some transformations, like if we subtract 2 from it, that might change the domain and etc. Okay. But before we do this next one, I just want to say one last thing. We've done a couple of examples on log base, log of different things. Log base 2 of this, log base 5 of this, log base 1/2 of this. There could be pretty much just any type of bases. However, anytime you have log base e of something, remember e is this fancy, a famous number. It's an irrational number. 2.71 approximately. It's just as famous as pi, except most people don't know about it, but it should be. E is about 2.71, and it goes on forever, and there's still decimals going on about that. But it is a famous irrational number. But anytime you have log base e, meaning of 2.71, it can also be written as it can also be written as natural log. That's an ln of x. Make it that's an L. Okay. So you could write log base e of x, or you could write just ln of x. Now ln stands for natural logarithm. And I always wondered why it's ln then. If natural logarithm is nl, it should be nl, not ln. But this was actually derived from the Latin word, and in Latin this word is backwards. It's logarithm natural, or however they would say it in Latin, and that's why it's ln. But anytime you see log base e, you can also rewrite it as just a natural log. And the cool thing about natural log is you also have a button on your calculator that says ln. So that's pretty handy. Okay. All right, so just keep that in mind. Okay, ln of x, same thing as log base e of x. You can write it either way. All right, example number 5, we're going to go ahead and graph a logarithmic function. The logarithmic function they give us is negative natural log of x minus 2. Now remember, you can always rewrite this as negative, and instead of ln, you could write log base e. It's the same thing of x minus 2. I just want you to keep in mind that these are equivalent statements. Just another way of writing that. Okay. All right, so first thing we're going to do is we're going to find the domain. Well, domain, just like we did on the previous page, pretty much just means whatever is inside the logarithm, just it has to be positive. So that's exactly what we're going to do here. ln or log base e, however you want to think about it. Whatever's inside the logarithm, or the natural logarithm in this case, has to be positive. So I know that x minus 2 has to be greater than 0. So all I have to do is solve for x. And I'm going to do that by adding 2 to both sides. Minus 2 plus 2, those cancel out. And I know that x is greater than 0 plus 2, which is 2. So my domain is just x is greater than 2. You can also write it as 2 to infinity if you want to write it in interval notation, but I'll just leave it as is. Now what that means that my domain, my x values, if you look at the graph, is only going to be from 2, from the x value 2 and on and greater. That means there's not going to be anything behind the x value 2. So pretty much this, everything before 2 is going to be pretty much be blank. There's going to be nothing going on. There won't be any graph there. The graph will pretty much start at 2 somewhere and it'll go on. I'm not sure where exactly, but it'll be here at 2 and everything after. So that's what the domain tells us about the graph. You kind of already know where your graph's going to be generally located. So that's just pretty helpful. I'm going to go ahead and just draw this vertical line because I know that this is where the graph's going to start. And it's also actually called the vertical asymptote, which we'll get into in just a bit. All right, now I still don't have a graph, but what you could do anytime you want to find the graph of something, you can always just plot some points. So I'll go ahead and make a little table, x comma y, and you can just pick some points for x. Now remember, x is going to start at 2, so you can try to pick points over here, but you won't get an actual answer, and you can try, but I already know my x values are only going to start at 2 and go on. So I'll go ahead and start my x value at 3. And my y value will be, we'll just plug in this 3 value for x. I'm going to go ahead and just use the first one. So negative natural log of 3 minus 2. And I don't know what that is, but I'm going to go ahead and type that in. Negative natural log of 3 minus 2. And I got 0. So 3 comma 0 is one of my points. I'm going to go ahead and plot a few more points. 4. When x is 4, my y value will be negative natural log of 4 minus 2. I'm just using this equation up here to get my y value. Is equal to, let's see, negative ln of 4 minus 2 is negative 0.69, which 4 comma negative 0.69 is somewhere right here. Okay. When x is, I'll just do 5, my y value will be, and I'll just go ahead and type it in, negative ln of 5 minus 2 is negative 1.0986. So if I try to plot that, it's 5 down negative 1.09, somewhere right there. It doesn't have to be perfect, but you get the point. And you can make a few more points if you'd like, but I kind of already see what's going to happen once I connect all these points. The graph is going to look something like that. And there's our graph. Now it says from this graph, figure out what's the range and what's the vertical asymptote. Now vertical asymptote, we kind of already have that made. That's this line, x equals 2. This 2 is just like this vertical boundary line. The graph never kind of goes before it, behind it. So the vertical asymptote would just be x equals 2. It's this vertical line that the graph kind of has as a boundary. And the range is just the lowest the graph goes and the highest. The lowest the graph goes, and I probably should have made a few more points, but the lowest the graph goes, it kind of starts to hollow out at this horizontal line, which is negative 2. So the range would be the lowest the graph goes is negative 2, and then there is no highest point the graph goes. kind of goes up in the upwards direction forever, so that would be our range. I kind of wrote that all over the place, sorry. And there's our graph. Okay. All right, moving on to the last page. Now we're actually going to solve just a few logarithmic equations. So we've kind of learned a little bit about logarithms, how to convert them from exponential to log form. That one's very useful. How to graph them, how to find the domain of them. And the last part is how to solve equations that have them. Now, before we do these last two examples, I just want to say one more thing. This one's a pretty important one. Sometimes the base isn't written. Like on all these problems, you had a base log base 2, log base 5, log base 1/2. The previous one even had log base e, which can be written as ln. But there's so many different bases that you can put on a log. Sometimes, if you look at this one, the base isn't written. It just says log of x. Now, logs always have a base, even if it's not written. Now, in this case, when the base is not written, the base is always 10. So see how the base is not written? This could also be rewritten as log base 10 of x. So when the base is not written, the base is 10. That one's very important. This is called the common logarithm. I know there's a lot of rules to keep in mind because this is all new to us, but just at least have it down. But I'm going to go ahead and write that. When the base is not written, the base is 10. And the cool thing about base 10s is because that's actually the only one that our calculators can actually calculate. If I typed in log of some number, I'm not sure, just any number, I can type it continue. There is no base automatically written because that means the base is 10. That's actually the only type of logarithms your calculator can calculate. So that's pretty nice when the base is 10 because I know I can use my calculator for those types of problems. Okay, but just keep that in mind. When the base is not written, the base is 10. Okay. All right, example number 6. We are given this logarithmic equation and we need to solve for x. I could try to sit here all day and plug in numbers that might work for x, but that might take a while. So instead, just by looking at this really doesn't help me at all. I don't know what x is, and I don't even know how to solve for this logarithm because I can't use my calculator for these types of functions. So what I can do, though, since this helps me in no way just by looking at this in logarithmic form, first thing I'm going to do is when it doesn't help you in log form, convert it to exponential form. It's not helping us in any way in this form, so maybe if we convert it to exponential form, it'll be a little bit more useful. Now, if you're wondering, how do we do that? Well, we did it on the very first page of the notes. You are given a log form, convert it to exponential form. So we're doing that same thing. Start with the base, which is the little number on the bottom, which is 3. Raise it to the second power, and set it equal to whatever's in the logarithm, which is 4x minus 7. Now this one's a little easier to work with. We know how to do stuff like this. We can just solve it. 3 squared, that's just 3 times 3, that's 9, equals 4x minus 7. And then you're just solving for x. This is just a linear equation. So I'm going to go ahead and start by adding 7 to both sides because I'm trying to solve for x. Minus 7 plus 7, that's 0, so let's just cancel out. 9 plus 7 is 16. And I'm going to set it equal to 4x. And then lastly, I'm just going to divide by 4 so I can get x by itself on both sides. 16 divided by 4 is 4 equals, and 4 divided by itself is just 1, so those just cancel out, x. And there's our x value. Okay. So if we wanted to, you can always check equations, check that your answer is right, by plugging in this 4 for x, and you should get a true statement. So if I wanted to, you could plug it in log base 3 of 4 times 4 minus 7. And you want to see, does it equal 2? Well, if I did the math, this would just be log base 3 of 4 times 4 is 16. 16 minus 7 is 9. Let's see, this just means, does 3 raised to the second power equal 9? Yes, that is true. So if you wanted to, you could always check that this answer was correct by plugging it into your original problem. All right, and then part B, again, we want to solve this logarithmic equation for x. We want to figure out what is x equal to. Well, in order to do that, right now it's not really helping us much just by looking at it in log form. It doesn't tell us much. whenever it doesn't tell you much, whenever you can't do anything in log form, it doesn't make sense, you can't solve it easily, you can't type that in because you can't type in the log of base x, we can always try converting it to exponential form, and maybe it'll be a little bit more useful to us in that form and easier to solve. Now we know how to convert to exponential form. That's what we practice on the whole first page. Start with the base, which is this little number on the bottom, which is x. Raise it to the second power. Set it equal to whatever's inside the logarithm, which is 64. All right, so what we have now is we have x squared equals 64. All right, I'm going to solve for x, and I just need to get rid of the second power. So the opposite of second power, or square, is square root. So we're just going to take the square root of both sides, because square root and square, they cancel out. They're inverse operations. And we're just left with an x equals, now the square root of 64 is positive or minus 8. Anytime you take the square root, it's always technically positive or minus. So we have two answers, positive or negative 8. But remember that one rule that I said on the front, the base has to be positive. So x is the base, so we can't have it equaling to negative 8. It can only be equal to positive 8. So really, we just have one answer, and that is 8. Because it has to be positive base. Okay. All right, last problem, example number 7. This one's a little bit of a challenge one. Solve for x. Now, this time it gives me an exponential equation, and it says to solve for x. Remember, e is that famous number. It's approximately like 2.71. It has a bunch of decimals. It goes on forever, and it's still going on, but that's approximately. E raised to the 2 times some number equals 5. Now, that really isn't useful to us in that form. I can't even get x by itself because there's this e and this 2 that we don't really know how to get rid of. But when that happens, when something's not useful to you in exponential form, what we can do is let's see if we can convert it to logarithmic form and see if it's useful to us in that form, if it's easier to solve. Sometimes a problem is easier to do with an exponential form, so you want to convert to exponential. Sometimes it might be more useful to be in logarithmic form, so that's why you'll convert to logarithmic form. So that's what we're going to do. And the way this would be written in logarithmic form, it would be log. Your base is whatever has an exponent on it, which is e, rate of 5, and then set it equal to the exponent, which is 2x. Now, you can leave it like this, but remember, log base e can also be written as natural log of x. So if you want to write log base e, that's fine, but you can also just write natural log, ln, that's a L, of 5 equals 2x. It's the same thing. It's another way to write log base e. I like it in this form. The reason why is because ln, I can actually use my calculator to calculate those. I can just type in the ln button of 5 and it'll calculate that for me. I'm not typing in any x's or unknowns that the calculator doesn't know how to do. I'm just typing in numbers. And I get about 1.6094. I'm going to go ahead and just round. Just write it right here. 1.6094. And I'm rounding, so I'm going to use these symbols, approximate symbols, instead of an equal sign now. It's approximately 2x. I haven't done anything with that. I'm running out of space, so let me write it up here. All right, I'm almost done. I just need to solve for x, so I just need to get rid of this 2. And the way I would do that, let me just rewrite the problem. 6094 is approximately 2x. I'm just going to get rid of this 2 by dividing both sides by 2, because 2 is being multiplied by x, so we would just divide by 2. 2 divided by 2, that's just one whole. They cancel out. And my x value is 1.6094. I'm just going to leave it typed in, divided by 2. Enter. And there's our final x value, about 0.847. Oh, I think I messed up. 0.8047. There you go. Is approximately our x value. And there's our answer. And you could always plug it in. If you want to go back and try to plug it into your original problem to check, you could. E raised to the 2 times 0.8047. Now we're rounding, so we won't get an exact answer. Is about 5, which that's pretty close to 5, so that's a good way to check. And there you go.